So I thought it would be productive to talk a little bit about oxacyclopropanes, which are also called epoxides. That's the term you'll probably see most often. And oxiranes, that's the IUPAC name for it, but you will not really find very many people talking about these things as oxiranes. What we're talking about here is a three-membered ring that contains oxygen. So it's a cyclic ether. Ethers are usually pretty unreactive, but because of ring strain, when you have a ether that's constrained into that three-membered ring, right, these carbon-oxygen bonds are weaker than normal. Which means that they can break even though the alkoxide ion is a terrible leaving group. And they can break either by SN2 or by SN1 pathways, depending on whether the oxygen is leaving as a negatively charged atom or whether you protonate it first and have it leave as a neutral atom, right? So negative charged leaving group, the alkoxide, and SN1 protonation first, and then a neutral leaving group. But the stereochemical outcome and the regiochemical outcome is going to be different. Actually, the stereochemical outcome is not going to be different. Both of those reactions go with inversion, but the regiochemical outcome is going to be different depending on whether you're doing an SN1 type reaction with a negatively charged leaving group or an SN1 type reaction with a neutral leaving group after protonation. So why are those carbon-oxygen bonds weaker than normal? What is it about those carbon-oxygen bonds? If I asked you to draw a picture to explain why those carbon-oxygen bonds are weaker and more readily broken than usual, what would you write?
Does it have to do with ring strain?
It does. I mean, yes, the reason why they're weaker than normal is because of ring strain. So you've just rephrased the question. The question now is explain the origin of ring strain, right? Which was something that we've done before.
It's the 60-degree bond angles.
So it's the bond angle strain, right? That's the major component of ring strain. There's less eclipsing than there would be in a cyclopropane because the oxygen doesn't actually have any hydrogens on it. So there are only 2 eclipsing interactions instead of the 6 that there would normally be if it was a CH2 group. So the major source of ring strain is the bond angle strain, and that's even more true of the oxacyclopropanes than it is of the cyclopropane. So what we'd want to do is we'd want to draw, once again, the orbitals that are overlapping at an intra-orbital angle of about 109.5 degrees. And I haven't shown it here, I'm just showing a regular single bond there. So we'd want to show that we're constrained into a 60-degree bond angle, but the angle between the orbitals is 109.5 because oxygen is tetrahedral, right? There's 4 electron groups on oxygen, 2 lone pairs, right? So that difference between the actual bond angle and the intra-orbital angle puts the pair of electrons that are forming that bond outside the bond axis where it's not able to interact. Right? It's actually a little known fact that's not really relevant to this class that because of where those electrons are in cyclopropane being outside the bond angle, it is actually possible if you have a strong enough acid, right? if you have kind of a super acid, it's possible to protonate cyclopropane. That pair of electrons will join and bind to the hydrogen, and you can get what's called edge protonated cyclopropane, which looks ridiculous, right? It looks like it's broken all the rules. It's got a hydrogen that's kind of attached to both those carbons. So now you've got the wrong number of bonds to things. And the overall ring is now positively charged because of this hydrogen bridging between the two carbons. So, right, it's pi-like, both in strength, right? It's 65 kilocalories per mole, and it's pi-like. Pi bonds can attack protons. Well, so can the pair of electrons, which isn't really a sigma bond, right? It's kind of, it's a partial bond here. So you've got that edge protonated cyclopropane, and that makes cyclopropane rings more reactive. But anyway, once we have that down and we understand why the oxacyclopropane is reactive, we can understand how nucleophiles, if it's a strong nucleophile, like something like lithium aluminum hydride, for example, the lithium is a spectator ion, the aluminum hydride is the reactive, right? So this is a nucleophilic hydride, kind of an H minus. That can come in and attack, and it will do it at the less hindered carbon, which means it will want to attack this carbon, which is the CH2 group, rather than fighting with this methyl group to attack from the back side, right? It's SN2-like, so it's coming from the opposite side. It's pushing that group out, and the product will have a CH3 group here now, and it will have kicked out the the alkoxide ion, and we will not have changed the stereochemistry at this carbon. So the methyl group will still be pointing out, and the hydrogen will still be pointing back. We will have actually inverted the stereochemistry here. So if this was a deuterium, for example, right, we'd be able, well, we wouldn't be able to tell because it's a CH2 group. But we won't have inverted the stereochemistry here. What's the stereochemistry of this carbon? Is it R or S?
S.
Yep. So oxygen is your first priority. This carbon, because it's attached to oxygen, is second. It's 3, hydrogen is 4, and it's still S. Right? And then, as always, when you do a lithium aluminum hydride reaction, right, the first step is lithium aluminum hydride in diethyl ether, and then in the second step, we have aqueous acid. Right? We can protonate that to generate the alcohol, and we will have generated, actually I guess it's not still S unless that's deuterium, but if that's deuterium then it's still S. Oops, sorry. Right. So, simple protonation step, aqueous acid being attacked by the double bond. Right. So any strongly nucleophilic reagent will attack at the less hindered carbon by an SN2 pathway. Doesn't have to be lithium hydride. It could be a Grignard reagent. It could be like a CH3S minus, something like that. If we react it with an acid, so if instead of reacting it with a strongly nucleophilic reagent, we were to react this with, say, concentrated HBr, aqueous, which is 48% HBr. First step would be for that hydronium ion to get attacked by the lone pair on the oxygen. To form an oxonium ion right. And now we have the possibility of a neutral leaving group, but it doesn't leave all the way. It kind of starts to leave, but then this oxygen stays kind of hovering over the top, which means that the second step is actually stereospecific. Right? Which is not normally what you would expect for an SN1 type reaction. For an SN1 type reaction, you would normally expect the second step to go with racemization because you'd expect a carbocation intermediate. There's no actual carbocation intermediate. So bromide is going to come and attack, and it will invert the stereochemistry there to generate an alcohol. Oops. Water left. Sorry, messing up. Right, it will generate the alcohol with the bromine down. So if you were to make one of these hydrogens a deuterium or something so you could distinguish the two methyl groups, you would notice that you'd actually inverted the stereochemistry. So we get inversion of stereochemistry in both the SN1-like reaction. It's not truly an SN1. It's kind of SN1-like because of the stereospecificity. But we get unimolecular kinetics, first order observed kinetics, just like you would for an SN1 reaction, as opposed to the bimolecular kinetics. And we get reaction at the more substituted side. So regiochemically, it matches, because of hyperconjugation, it matches what you would expect for an SN1 reaction. So with strongly basic, strongly nucleophilic reagents, inversion of stereochemistry at the less substituted end with a negatively charged leaving group, right? Sterics runs the day here, attacks at the less hindered carbon, stereospecific inversion with acidic reagents and less good nucleophiles, like if you had just methanol and a little bit of catalytic acid, you get reaction at the more substituted end, but still stereospecifically, right? Still inversion of stereochemistry because the carbocation is actually not there. It's like the helicopter parent. The oxygen is kind of sitting over the carbon saying, you sure it's okay that you're positively charged? Did you put your raincoat on? Are you wearing the right shoes? Right? It's just kind of hovering there until the bromide comes in, and then it feels comfortable enough to leave. So that's not that obvious, I think, and maybe the video didn't make it 100% clear. That would have been the second to last of the videos in the playlist. I just wanted to go over